So far, we have explored the basics of human language, natural language processing, tokenization, text data pre-processing, and embedding techniques. In this video, we are going to talk about large language model, why they are really called large language models, the history of the language models, and the large language models which are available in the market. This video is part of Zero to Hero in NLP, LLM, and GenAI, and this course is designed for someone who really wants to start from zero. Keeping in mind that someone may start really from zero, so to explain what is LLM or a large language model, I thought breaking this into what is language model and then talk about what is large language model. So let's begin. You must have noticed in your email application there is a spam folder and some emails are automatically moved into that folder. This is achieved through a trained language model which is doing that specific task. So how that training happens? We again start with a deep neural network algorithm, a piece of software code like this. All these nodes which you see here are the nodes which is nothing but different functions to learn some pattern in input data. A deep neural network algorithm is fed with samples of spam emails and non-spam emails. The algorithm's primary function is to learn patterns within those sample emails and store the learned patterns in the memory and produce an output called trained model. Then we test this pre-trained model with new emails input data to check if it is able to predict if this email is a spam or not spam. In this input data, email 2 was spam, but the model predicted it wrongly. It tagged email 2 as a good email and email 1 and 3 as the spam email, which is incorrect. When we realize that it is still not up to the mark of identifying spam email, then we further train with more input data. Let this deep neural network learn more patterns and let it update its memory with more learned patterns, also called parameters. It will produce a new model. Get that updated model and again validate with new input emails. Finally, we get our pre-trained language model trained, which is successfully able to detect spam in the email. So like this, finally, we get our pre-trained language model for one task, which is to detect spam in the email. So this is how language models are trained and language models are produced. So like we pre-trained our language model for spam classification or spam detection, we can pre-train different language models for different tasks, such as translation, information extraction, question answering system, social media analysis, and many more language specific tasks. Everything appeared to be going well, but there were challenges. The architecture which was used inside this deep neural network architecture was RNN, called recurrent neural network, and the another one was LSTM, long short-term memory. Both struggled to handle large sequences of text, like long paragraphs or essay. By the time it got to the end of the paragraph, they would forget what happened at the beginning. Such behavior can impact use case result. For example, in machine translation task, see this example where there is an English sentence, which is the hotel is located near the bank of the river, offering breathtaking views and a serene atmosphere. In this example, the RNN might mistranslate bank as a financial institution instead of intended meaning, which is the side of a river. This occurs because RNN face challenges in capturing long distance dependencies and maintaining a coherent context, especially when the translation involves complex sentence structures or nuanced word meanings. Take another example, sentence completion task. Here, the language model is trained to predict the next word in the sentence. This task requires context understanding. Let's take this example sentence. LSTM have memory cells that can capture short and long-term dependency to some extent. But as the sequence grows, they might struggle to retain relevant information from the beginning of the sentence. As a result, this LSTM might have difficulty connecting the word hidden cave with the earlier context like an old treasure map, potentially affecting the accuracy of predicting the next word, and it might predict a word rock instead of hidden treasure. This limitation in capturing very long-term dependencies can impact the model's performance in tasks that demand a comprehensive understanding of context over extended sequences. Another challenge with this architecture were like both used to process text data into sequence. That means these models were hard to parallelize during training. This meant you could not just speed up training by throwing more hardware at them, which meant in turn that you could not train them on a humongous data. So to sum up, the key challenges were a struggle to handle large sequence of text, limited context understanding, and lack of parallelization, that it cannot scale the training process by throwing more hardware to it. Then came 2017, this white paper called Attention is All You Need, a new architecture called Transformer for deep neural network algorithm. It was proposed by Ashish Vaswani and group of researchers at Google. We all should feel proud because Ashish Vaswani is an Indian. This transformer architecture in language model is a groundbreaking design characterized by self-attention mechanisms, enabling efficient processing of input sequences. It utilizes attention mechanism to weigh different part of the input text, facilitating context understanding. Because it also supported parallelism, so during training, the deep neural network will try to learn the pattern or features of each word independently against entire word in the whole corpus and not just few surrounding words, which was the case in RNN and LSTM. Therefore, using transformer architecture, problems associated with RNN or LSTM was resolved. So now with transformer, we can utilize large computational power and do parallel processing during training. Because of this parallelism, we can now feed large training data, maybe the entire internet data, during the training phase. And deep neural network utilizing transformer architecture can learn large complex pattern, also called parameters or weights, utilizing large memory to store these patterns. With all these language models can now learn and memorize entire information freely available on internet. And the language model can take a leap to large language model. This is why it is so called large language model. The landscape of language modeling has undergone a transformative shift with the advent of large language model. The traditional approach depicted on the left side involved training separate language models for distinct tasks. In contrast, the new approach places the large language model at the core, harnessing its enhanced power and capabilities. This new approach involves constructing task-specific applications around the central model through techniques like prompt engineering and fine-tuning, making a departure from the conventional isolated training methods. We will talk about prompt engineering and fine-tuning in separate video. These are some more historical details about large language models. It provides their release dates, name, who published it, number of parameters, also called weights, which is nothing but the number of learned patterns they have, then corpus size on which they are trained on, and the usage license. This data is collected from Wikipedia. I will provide the link of that Wikipedia page in the description.